You good? That was fast. YouTube always takes a while. Come on. YouTube, where's the link? Yeah, there we go. And I just need the chat. Yeah, I guess we're good to go. I do want to check. Testing. Okay, I mean, it's a bit slow. It works. Okay, it's fine. What about this one? Test 1 2 1 2. Okay. Guess that works. Yeah. Okay, perfect. Oh, now it's going to be on the screen. Maybe I can delete. Dump in this. Clear chat. Nah. Well, fine. It's just going to be there. Okay, I think yesterday I read up to here. To be fair, I can't remember most of the things I read yesterday. Anywho, there's a long way to go. Probably just carry on. Okay, virtual machines and real machines. I do find this interesting. I like the whole simulation testing thing. So maybe if I can, maybe if I can understand virtual machines, just maybe I can build a simulation. Yeah, that's what I was thinking. These are programs that emulate a computer, including hard drive graphics. They allow you to run a different operating system inside. But these are not the ones we're talking about. That's the other type of virtual machine. Excuse me. What are we going to talk about? Our virtual machines, and later build our virtual machines that are used to implement programming languages. Sometimes they consist of just a few functions. Other times they make up a few modules. On occasion they're a collection of classes and objects. It's hard to pin their shape down. That doesn't matter. What's important is this: they don't emulate an existing machine. They are the machine. Excuse me. It's important. They don't emulate an existing machine. They are the machine. Not sure what that means. The virtual is due to the fact that they only exist in software, not in hardware, and are thus purely abstract constructs. The machine describes their behavior. These software constructs act like a machine, and not just any machine, no, they mimic behavior of their hardware equivalent, computers. Not sure what that means. It means in order to understand and build a virtual machine, we need to learn how a real machine works, I guess. So, how does a computer work? Good question. Might sound like an intimidating question. This question can actually be answered in 5 minutes and with a piece of paper. Don't know how fast you can read, and I'm certain I can't show you what I draw on a scrap of paper, but let me try anyway. Nearly every computer in your life is built according to von Neumann architecture, which describes a way to build fully functioning computer with a surprising tiny number of parts. In von Neumann's model, what is this? Von Neumann architecture. Where both data and instructions are stored in the same memory. Bit architecture based on that. Time patterns, the attribution. Okay, it's just a bunch of facts. That's what I usually find with Wikipedia. Never mind, I'll just continue. Maybe he explains it. In von Neumann's model, a computer has two central parts: a processing unit, which contains an ALU and multiple process registers, and a control unit with an instruction register and a program counter. Together they're called the CPU. Okay. Processing unit contains an arithmetic logic unit and multiple processor registers, and a control unit, then instruction register and a program counter, called the CPU, central processing. Often shortened to CPU. Besides that, the computer also contains memory, mass storage, and I/O. CPU, memory, mass storage, and I/O. Okay, CPU, memory, mass storage, and I/O. Input, memory, CPU, mass storage, or back to memory. Output. As soon as the computer is turned on, the CPU fetches an instruction from memory. The program counter tells CPU where in memory it can find the next instruction. Decodes the instruction to identify which operation should be executed. Executes the instruction. This can mean either modifying the contents or transferring data from registers to memory, or moving data around in memory, or generating output or reading input, and then go back to 1 again. Okay. Fetches an instruction, decodes it, executes the instruction. Fetch, decode, execute. These 3 steps are called fetch, decode, execute cycle, or instruction cycle. I never knew that. I've always heard instruction cycle. Yes, that's the cycle known from sentences like sentences. Okay, forget. Like the clock speed of a computer is expressed in cycles per second. 500 megahertz, or we're wasting CPU cycles here. So it means this cycle. Oh, that makes sense. That's why it's called a cycle. Again, you learn something new every day. Probably have used that word maybe, let's say 100 times or more. I had no idea what I was talking about. just realized. So full of shit. That was a brief and easy to understand description of how a computer works. But we can make it even easier. In this book, we don't care about mass storage. Who cares about mass storage? Components, and only tangentially about the I/O mechanisms. What we're interested in. What we're interested in is the interplay between CPU and memory. This means we can make that our focus and safely ignore hard drives and displays. Yeah, fuck displays. They're gone too. I mean, you take enough of this stuff out. Not too bad. We start our investigation with this question. How does the CPU address different parts of the memory? Or in other words, how does the CPU know where to store and retrieve things that are located in memory? What's the question again? How does CPU access? Yeah, I've always wondered this too. Different parts of the memory. Or in other words, How does the CPU know where to store and retrieve things that are located in memory? Guess this is what the OS does. Allots a region of memory that you can use in your program. That's what I remember from. This reminds me of what every, yeah, this one. Thing he, oh, there's no index, but he does mention quite detailed. Pretty good. We have never read it before. Okay. Where was I? Yeah, okay. We're given a hint by how the CPU fetches instructions. Program counter, part of the CPU, keeps track of where to fetch the next instruction. And counter is to be taken quite literally here. Computer simply uses numbers to address different parts of memory. Yes, numbers. Okay. Must need a lot of numbers because memory is quite big, right? At this point, I'm tempted to write. Just think of memory as a huge array. It's not entirely wrong, is it? But I'm scared of someone hitting me over the head with a heavy leather-bound tom called Things About Memory that are absolutely and without any doubt not like an array, you doofus. Okay. We don't want that, do we? So I won't, but yes. Just like we as programmers use numbers as indexes to access single elements in an array, CPU uses numbers. Instead of array elements, computer memory is segmented into words. Word. Now, what's a word? Then it's, what's it called? Is it the size of the address? Or like how big the address can be? Or the addressable space? One of the two has to be. It's the smallest addressable region of memory. Pretty close, 50-50. Addressable region of memory. It's the base unit when accessing memory. The size of a word varies and depends on the CPU time, among other things. In the computers you and I use, however, 32 and 64 bits, word sizes are the standard. Oh, okay. I just realized. Something I read. I think it was here. Any Opaque. Mm-hmm. Is this why? No, no. I think it was something to do with pointers. Can't remember where I read it. It was something along the lines when you pass during comp time in Zig, it has to know what the size of the variable is. So that's why pointers are fine. Any opaque pointers are fine because pointers have fixed size, or the memory they point to. Something like that. It's quite interesting. I like it. Let's say we have a fictional computer with a word size of 8 bits and 13 bytes of memory. One word in memory can hold one ASCII character, and if we store the string hello world to memory, it looks like this. 8 bits and 13 bytes. Oh, okay, sorry. I read it wrong. So it's like the word size is 8 bits and it's got 13 bytes of memory. Okay. The letter H has the memory address 0. I don't know why I fidget this fucking mic so much. It's never in the right place. Maybe because I'm moving. Okay, where was I? The letter H has the memory address 0. E has 1. The first one. Hey Toby. Quest. I don't know. It's pretty good actually, I would say. I'm learning a lot of new things, and I'm realizing I was full of shit when I was using words like CPU cycles. I just realized I had no idea what it actually meant. So yeah, it's turning out to be a humbling experience. Because every time I thought of CPU cycles, I thought it was just execution. Oh, seems straightforward. Yeah. Will do. Definitely. I am guessing you've built VMs before. Okay, nice. Maybe We go on a side quest and then build a virtual machine. I think in the book it's part of the compiler. You build the VM first. Excuse me. Now, where was I? Other than a compiler. I had maybe you know something about this. You know when people do like simulation testing, are they talking about virtual machines as well? Or that's completely different? Hello, Commander. What do you mean this is not day 2? Well, I mean, I started yesterday. Okay. Yeah. I did as much as needed to be able to start working on the compiler. The interpreter? Yeah, it can... What can it do? Yeah, it can parse, create an AST, and parse tokens. So the execution is ready for execution. Does that make sense? Well, not completely works because it can't parse function calls. Simulations do not usually simulate virtual computers. No, my question was, when they say a simulator, is it a virtual machine? Like virtual machine of the actual machine? Commander, no, it doesn't evaluate. That's what you're asking. It's going to be a compiled language, so I didn't do the evaluation. It's not unless a simulator of a game console or something. Okay. The interpreter was like step 1. Because I think you still need to do lexing and parsing. So yeah, I didn't want to do evaluation because it's not that hard, right? Because Zig already has all the built-ins. So I'd just be calling Zig functions. Yeah, it is. Well, I should have been clear. Should have said built-in part of an interpreter. To be fair, I think I should never have called building interpreter. Just needed the lexer and the parser. Excuse me. So far, I do like the compiler. I mean, virtual machine, sorry. Sounds quite exciting. I'd definitely like to build one. Okay, where was I? The letter H has memory address 0, E has 1, L is 2, and so on. We could access every single letter of string hello by using memory address. Hey CPU, fetch the memory address 4. Would result in, oh, straightforward, right? Know what you're thinking right now, and yes, if you take such a number, a memory address, and save it to another place in memory, we create a pointer. That's the basic idea behind addressing data in memory and how the CPU knows where to fetch and store data. As always though, the real world is a mess. No shit. As I already mentioned, the size of a word differs between different computers. Sometimes it's 8 bits, sometimes 64, and on. Sometimes the word size used by the CPU is independent of the address size. Really? I did not know that. And if that's not enough, some computers do entirely different and use byte addressing instead. What the fuck is byte addressing? Stack Overflow. See what it's got. Five to 10 bits depending on the machine. Word had 12 to 60 bits. Address words of memory processing text. It's rather difficult. Word machines would typically store a bunch of characters in each word. To work on strings, you couldn't use pointers as strings. Could begin or end in the middle of a word. Yeah. This necessitates some rather complicated programming. This was okay back when computers used to do arithmetic and very little text. But text became blah blah blah, completely pushing word machines out of the market. By word machines, does he mean DSPs, but they're significant normal languages, blah blah. Doesn't directly need them. For example, if you want to load a byte, you would load a word, then use bit shifts and masking operations to fetch the byte you wanted. Similarly, to store a byte. Okay. Guess it kind of makes sense in where there's not a lot of memory. Maybe. Not sure what it means. Each address was a byte. Tiny. So that means if you store ASCII, you store one letter at the address. Seems like a lot of work. Okay. And if you're using word addressing, I want to address a single byte, which is not that uncommon. You not only have to deal with different word sizes, but also work with offsets. That in turn is expensive and has to be optimized. Using word addressing, I want to address a single byte. Yeah. I have to deal with different word sizes, but also work with offsets. Okay. Top of that, the idea that we can simply tell the CPU where to store and retrieve data in memory is something like a fairy tale. It's correct on a conceptual level and helpful when learning, but memory access today is abstracted away and sits behind layers and layers of security and performance optimizations. Memory is not the Wild West anymore. Can't just go around and access any memory location we want. Security rules and a mechanism called virtual memory try their best to stop that from happening. Okay. Let me stop right there. Before we take a huge detour and end up talking about the inner workings of virtual memory, what you can take from this excursion is that there's more memory to access today than passing a number to the CPU. Not only are there security rules in place, the last few decades, computing has emerged a set of less strict conventions around the use of memory. In the last few decades of computing, emerged a set of less strict conventions around the use of memory. Okay. One novel aspect of the von Neumann architecture was that a computer's memory contains not only data, but also programs, which are the CPU instructions that make up a program. What? Computer's memory contains, okay, not just data, but the program itself. Yeah. Oh, I know. I think I know that. It's called don't know what it's called, but I do remember reading it. Mixing data and code sounds like a recipe for tears. And to the ears of programmers few generations ago, sounded like that too. But what they did was establish conventions around the use of memory, and that stopped that from happening. Well, so what they mean by instruction set and data set. Say memory as any other data, there is they're most often not stored in the same locations. So there's also, yeah. Okay. Dumb data, as in the contents of a text file or the response when HTTP request goes in one region of memory. The instructions that make up program are stored and accessed in another region where the CPU can easily fetch them. Excuse me. Another region holds the static data that's used by a program, and yet another region is empty and uninitialized, but reserved so that it can be used by a program once it's running. The instructions belonging to OS kernel have their own special region in memory. Okay, this is quite long. It's a lot of reading. Okay. All right. I can do this. By the way, while programs and dumb data may reside in different memory locations, the important here is that both stored in same memory. Right. Data and programs are both stored in memory. Make it sound as if they're distinct, when in fact programs made of instructions are just data too. Yeah. Instructions only become instructions, once the CPU fetches from memory, decodes them, finds out what they are, and then executes them. If CPU decodes data that is not a valid instruction, the consequence will depend on the CPU design. Could trigger an event and give the program a chance to recover, or it could just stop. For us, the most interesting thing about this is one particular memory region. It's the memory region that holds the stack. Yes, this stack. Drum roll, fanfare, blah blah blah. The stack, you might heard of him. Stack Overflow is probably his most famous work, followed by the less popular but equally respected Stack Trace. It's a region in memory where data is managed in a LIFO manner, last in, first out. The data in it grows and shrinks. You push elements onto the stack and later pop them off, just like the stack data structure. But unlike the generic data structure, the stack is focused on one purpose. It's used to implement the call stack. Okay, what is a call stack? Funny you should ask. Oh, I thought he was gonna. That would have been nice. Stack data structure, call stack. Not really self-explanatory, is it? Often used interchangeably. Okay, we have a memory region where the CPU accesses and stores data in a LIFO manner. Yeah. Okay, a region in memory that the CPU stores shit. Right. It's called call stack. Okay. Why does it need a call stack? Because the CPU needs to keep track of certain information in order to execute a program. Call stack helps with that. What information? Good question. First and foremost, which function might need a lot of water today. It's actually quite interesting. I like it. First and foremost, which function is currently being executed and which instruction to execute next. Once the current function is executed, this piece of information, which instruction to fetch after the current function, is called the return address. Whoa. What's that again? This piece of information, which is the instruction to fetch after the current function, is called the return address. Ah, okay, gotcha. Okay, gotcha. So where the CPU returns to after executing the current function. Without this, the CPU would just increment the program counter and execute the instruction at the next higher address in memory. And that might be, yeah, could be not ideal. Okay. Instructions are not laid out in memory in order of execution. Yeah, next to each other. Imagine what would happen if all the return statements in your Go code would vanish. Okay, that's why CPU needs to keep track of return statements. The call stack also helps to save execution and relevant data that's local to functions. The arguments of the function call, the arguments of the function call, okay, like the scope of it. Okay. There's a lot of thing in that stack. So is it called the call stack? Because when you call a function, it has all the related piece of information to execute it and then where to go back to after. Not sure. So yeah, the return statement, return address, argument, and local variables. You could save, theoretically, you could save this information in any other accessible part of the memory in any way we see fit. But as it turns out, using a stack for this is perfect because function calls are often nested. When entering a function, the data is pushed onto the stack. Yeah. And while executing the current function, right, there's no need to access the local data of the outer calling function. It's enough to just access the top part of the stack, so to say. Not really sure. Could read that again. When entering a function, data is pushed onto the stack. And while executing the current function, there's no need to access the local data of the outer calling function. Need to access the local data. Do you mean the instructions? Well, it has more than instructions. It's enough to just access the top part of the stack, so to say. And once the current function returns, the local data is simply popped off. There's no need for it anymore. That leaves us with the local data of the outer function on the top of the stack. I don't know, I'm a bit confused. I'm not really sure. I understand what's going on there. I mean, as you execute each function, let's say one's nested within the other. Function 1, function 2. Function 1 gets pushed onto the stack. So you don't pop function 1 before you execute function 2. What's the top part of the stack? Okay, so it stays on the stack till it returns, which makes sense. Alright, sometimes going ahead helps. That's why we need the call stack and why it's implemented as a stack. The only question now is, why the notorious name? Why is it the stack and not just, well, I guess blah blah blah. What? Because using this region of memory to implement a call stack is a convention so strongly held and widespread that by now it's been cast into hardware. Certain CPUs support instructions solely for pushing and popping things on the stack. Certain CPUs support instructions. Okay. Every program that's running on them makes use of this memory in this way to implement this mechanism. There's no way around it. That's why it's the stack and not just, oh, the stack. Good. Okay. Oh fuck. I mean, it's not too bad, I would say. But there is a lot of fucking reading. Okay, but not too bad. I think chapter 2 looks much better. Fuck, where was I? Something to do with the stack. Alright, here. Oh my god. Guess I can read a bit more. I'll read till the end. Don't think I came very far. Okay, quite a bit. Not bad. Okay. But keep in mind that the concept of a call stack is just that. Can I ignore some of this? Okay, it's not bound to a specific implementation. Excuse me. With a specific memory region, one could implement a call stack in any other place in memory, but without hardware or OS support. Okay. In fact, that's what we're going to do. We're going to implement our own call stack, a virtual call stack. Interesting. I wonder why, if that's why it's called virtual. Because we don't... Interesting. Because it's in a part of memory which has nothing to do with the part of memory that would normally do these things. By normally, I mean here, with the hardware and OS support. Interesting. I mean, it's all okay. But before we do that and switch over to physical, from the physical to the virtual, one more concept. Okay, fine. You can imagine how often CPU needs to access this region of memory while executing a program. A lot. That means the speed with which the CPU can access memory puts a limit on how fast it can execute programs. And while memory access is fast, okay, it's not instant and still has a cost. That's why computers have another place where they store data. Oh yeah, the registers. This is L1, L2, L3. Yeah, I do have some idea about these. So does that mean I can just skip? Yeah. Okay, so that means in the virtual machine, we'll be building registers too. Maybe. Yeah. They're really small, but really fast because they are what they call process registers. Yeah. Yeah. What I know is I think L1 is the smallest memory, but it's the fastest. And I think it's the most easily accessible because it's the closest, or like it's on the CPU itself. Something like that. Something along those lines. A CPU of x86-64 architecture, for example, has 16 general purpose registers, each holding 64 bits of data. Oh no, this is not L1. Maybe. Registers are used to store data that's small but frequently accessed. The memory address pointing to the top of the stack, for example, is commonly stored in a register, top of the stack. That means top is mustn't, right, the start of the program. Specific usage, I gotta Google this. Process registers. Location available on the processor. Blah 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 blah. Maybe I can just, is it L1, L2, 3? Okay, there you go. Okay, so it's not the same. Okay, I don't think CPU registers. The BBC. I never thought the BBC is done for computer info. Are these the things that, what's it called, when you do, I mean the assembly code that I've seen got things like registers. You load stuff to register. Is this where this is going? Okay, so it's not what I thought it was. Not even close. Okay, I'll just read through it then. Processor registers are part of the CPU, and accessing them is much faster than accessing main memory. Might not store everything there, they're usually very small. Typically 1 word per register. A CPU of x86 that has 16 general purpose registers, each holding 64 bits of data. Registers are used to store data that's small but frequently accessed. The memory address pointing to the top of the stack, for example, is commonly stored in a register, commonly being an understatement. The specific usage of a register is so prevalent that most CPUs have a single designated register just for storing this pointer. Okay, interesting. Never knew that. The so-called stack pointer. Fascinating. The operands and the result of certain CPU instructions may be stored in registers. Okay, if CPU would need to add two numbers. Okay, yeah. This is where this is why I was thinking of assembly. So you load two numbers into the register and then you can add them. And then the sum will be stored in another register. Many more use cases for registers. So if there's a large piece of data frequently being accessed in a program, it makes sense to store the address of it to a register so it can be accessed by the CPU really fast. I'm going to read that again. There's a large piece of data frequently being accessed in a program. Okay. The most important one for us is the stack pointer. We'll meet that one soon again soon. Okay, I think that felt long. Oh, guess I'm only about halfway. Maybe, okay, I'll read one more section. Less reading for tomorrow. What is a virtual machine? Let me get straight to the point. Virtual machine is a computer built with software. So far, so good. It's a software entity that mimics how a computer works. Software entity. I'll admit, software entity doesn't say much. No, it says fuck all. But I use this phrase on purpose to drive home one point. Virtual machine can be anything. That was what Toby was talking about. A function, a struct, an object, a module, or even a whole program. What matters is what it does. A virtual machine has run loop that goes through fetch, decode, execute cycle. Just like a computer, it has a program counter. It fetches instructions, it decodes and executes them. Right. It also has a stack, just like a real computer. Sometimes it has a call stack and sometimes even registers. Hey, this sounds like a lot of fun. Can't wait to build this. Okay, we got a virtual machine. Easy. Got program counter, stack pointer, and a stack. Stack pointer will always be 0. As long as there's more instructions, you keep doing something. Yep. Current instruction. If it's a push, you push it onto the stack. Increase. Hey, wait a minute. What about the top of the stack? I thought that's what it was. Okay. Maybe not yet. So, okay. Ah, right. Just like, oh, it's like an assembly instruction. That makes sense because it is right now we're in the processor. Okay. If it's a push, we add. If it's add, we add the two numbers. Oh no, do we have to take them out? Yeah. Oh, so the numbers are removed and replaced with a new number. Interesting. And if it's a minus, we do the same. Pop both things off and then save this. Oh, by top of the stack. Okay, because it's the opposite. I was thinking the other way around. Okay, that makes sense. I mean, this was an easy virtual machine. I can do that. One iteration of this loop is one cycle. Right, because, well, in case of add, it's fetch. Well, this, no. Well, it's kind of decode, fetch, and execute. Oh no, it is fetch, decode, and execute. Okay. Yep. It has run loop that executes, fetches the current instruction pointed to by program counter, decodes it, and executes it. One iteration of this loop is one cycle. Yeah. Right. So this will push, kind of like pushing onto a register. We add the numbers. Right. So that would be 2. Nice. Okay. Yeah. Boom. Do I have to read the rest of it? Can I just skip? Oh, geez. Okay. Fuck it. Just read through it. Now, while that's an actual working virtual machine, it's rather simple. Like me. As you can imagine, it's not a showcase for what the whole spectrum capable of. You can write a virtual machine, but also in 50,000 lines. Right. Design decisions is whether the machine will be a stack machine or a register machine. It's so significant that virtual machines are grouped based on this architectural choice. Just like programming languages are sorted into, right? What's the difference? Put in the most simple terms, whether the machine uses a stack to do its computations. Okay, like the one above. Or registers. Right, okay. The stack machine, the stack machine and a matching compiler are said to be easier to build. The machine needs fewer parts and the instructions it executes are simpler. Right. since they only make use of the stack. The problem is that if you execute a load of instructions, okay, no. The problem is that you need to execute a lot of instructions because you need to push and pop everything on and off the stack in order to get anything done. Right. Yeah. Right. This puts a limit on how far one can take the cardinal rule of performance optimization. Instead of trying to do a lot faster, try to do less. Okay, didn't know that was the rule. Building a register machine is more work because the registers are an addition. It still has a stack. Thought I heard something. It's not as prominent as in a stack machine, but it's still necessary to implement a call stack. The advantage of a register machine is that its instructions can make use of the registers, and are thus much denser compared to the stack counterparts. I have no idea what I just read there. Can make use of the registers. Right. Instead of putting things on the stack, pushing and popping. Right. They're put on the registers directly. Program needs less instructions on a register machine than on a stack machine. Yeah, that would make sense. That in turn results in better performance, but then again, writing a compiler that produces such dense instructions takes more effort. It's about making trade-offs. Besides the main architectural choice, there's a myriad of other decisions that go into building a virtual machine. There are the big questions regarding how to use memory and how to represent values internally. Right. Then there are seemingly tiny things that turn out to be endless. Story of my life. In our example above, we used a switch statement to the dispatching in the machine. Yeah. In our switch statement, the implementation can be found right there. And while the switch statement looks like the obvious and only choice, it's far from it. When you're looking for maximum performance, you have to go in all the way. In there you find dispatching done with jump tables, with computed go-to statements, with indirect and direct threaded code. No idea what they mean. Because, believe it or not, with a sufficient number of case branches, a switch might be the slowest of these solutions. The goal is to reduce the overhead of dispatching so much that from a performance perspective, the fetch decode part of the cycle disappears. Oh, okay. That's probably why I thought it was just execute. They've just optimized it out of the equation. Okay, why build one? Guess I could read one more. Don't want to. I'm losing comprehension at this point. Fuck, it's only been an hour. What a lazy fuck. Okay, guess one more. Then I'll do bytecode tomorrow. Oh, it's almost there. Nice. This one seems like a... Why build one? Why would you build a virtual machine to implement a programming language? Even after I built a few tiny virtual machines and had read through source code larger ones, I still asked why. That's a good question. When we implement a programming, okay, no, it's not. But a second I was like, is LLVM just a virtual machine? But they specifically state it's got nothing to do with one. Should be able to execute all possible programs and not just functions we built into it. Universal computation is what we're after, and computers offer a solid model for it. If we construct a programming language based on that model, it's going to have the same computational capabilities as the computer. It's one of the fastest ways to execute programs. But if executing programs like a computer is the fastest way, why not just let the computer execute the programs? Portability, actually. I was thinking of the same. Like if you want your program to run on anything, or like more than one computer, you would want to probably generate the lowest denominator of your code that any computer can execute it. Yeah, that makes sense to me. We could write a compiler for our programming language that allows us to execute translated programs natively on a computer. These programs would be really fast. We would also have to write a new compiler for every computer architecture we want to run the programs on. That is a lot of work. Instead, we can translate our programs into instructions for a virtual machine. And the virtual machine itself runs on as many architectures as its implementation language. In the case of the Go programming language, that's pretty portable. I didn't get that last sentence. And the virtual machine itself runs on as many architectures. Ah, okay, I got you. So yeah, so since my virtual machine will be in Zig, the virtual machine will run wherever Zig can execute. Okay. There's another reasons. It's this: virtual machines are domain specific. That's what makes them different from non-virtual counterparts. Computers offer us a universal solution to all our computational needs and are decidedly not domain specific, and that's okay. That's exactly why we need a computer on which we want to run all sorts of programs. What if we don't need a machine to be that universal? What if you only need a subset of the features the computer has to offer? Programmers, we know that no feature comes without cost. Increased complexity, degraded performance are just two of the prices we regularly pay for them. Computers today have a lot of features. CPU on x86-64 supports between 900 and 4000 instructions. That includes at least 6 different ways to do a bitwise XOR on 2 operands. What the fuck did I just read? Computers today have a lot of features. 900 to 400 instructions. Right, okay. This is handy and what makes computers so versatile. But it's not free. The versatility has a cost, like every other feature. Think back to the switch statement in our tiny VM and take a second to ponder the performance implications of adding 3,997 more case branches. It's not going to end well. Is it easy to maintain the code or the program for this VM? The good news is we can turn this around. If we get rid of the features we don't need, we can go faster. Less complexity, less maintenance, less mass. This is where virtual machines come into play. A virtual machine is like a custom-built computer. It has custom parts and a custom machine language. It's tuned to a single programming language. All the unneeded features are stripped off, and what's left is highly specialized. Since you don't need to be as universal as a general purpose computer, you can focus. You can concentrate. Your efforts into making this highly specialized and custom-made machine work as best and go as fast as possible. The specialization, the domain specificity is as important as getting rid of the unneeded mass. Why this is so important becomes even more clearer when we take a look at the instructions a virtual machine executes. Something which we steered clear of up until now. Remember what we fed our tiny virtual machine? I do. Now what is that? What's push? What's add? What's minus? But these definitions are as toy-like and for illustration purposes only as the rest of the VM. They don't answer the larger, more interesting question looming here. What exactly do virtual machines execute? guessing it's bytecode. Okay, that's good. That's enough reading for one morning. But that was pretty good. It was a bit long. I quite enjoyed it. I learned a lot of new things. It's it's not the most entertaining thing to watch. It's quite entertaining to read. Okay. Short and sweet. I'm gonna call it a day there. Well, as always, thank you for hanging out, and I shall see you tomorrow. Have a good week. Oh, hey, Schoolie B. I was just about to leave. You caught me like, why Zig? I'm trying to learn Zig as to why. I don't know. I'm just curious. Seems pretty cool. Just want to try it out. That's it, really. Nothing specific. And I thought if I build a big enough program, I might understand it better. I plan on building one in Odin. I've heard of Odin, never I've seen the website. Yeah, I think, do you want to learn Odin, or is something you already know? Yeah, I'd say it's and by building one, you mean a compiler, I'm guessing. In building Ostrich DB in Odin. Nice. Sounds like a lot of work. Usually DBs are. Ostrich DB, yeah. Good guess. So how do you like the language so far? In your Ostrich DB experience? Okay, yeah. I think that was my first impression too. When I looked at the website, it looked very similar to Golang. I do like Go. That's nice to hear. What do you like about it? Odin, I mean. Manual memory management, standard lib is great, helpful community. Those are all good points, Schoolie B. I think it was my main motivation to learn Zig. I wanted to get decent at a language where I have to manage memory. So I just picked Zig because of I saw a talk by Tiger Beetle. I think it was one of their earliest talks. And yeah, I was like, that sounds cool, and I wanna learn that too. But at work, I use Go. It's easier. Yeah. Okay. Cheers, Coolie B. Yeah, I'll probably be reading some more before I write any code. But yeah, feel free to stop by anytime. Have a good day, mate. I'll see you later.